Hello, a very good morning, good afternoon, and good evening. Thank you for joining us today for the last talk of the evening for PEsidious, creating mutative evasive malware using artificial intelligence. Now, before I kick off this talk, I thought it'd be very fun to really explain what the word PEsidious means. I know I've had a number of questions pop up around this in the past, so I thought it'd be best to kind of get this out of the way in the very beginning this time. Now, for those of you who are Star Wars fans in the audience, you might have already figured this out, but for the rest, here's what it is. PEsidious is a portmanteau of two words, PE, which is the Windows PE executable, the primary data that we're working on for this project, and Sidious, who is .Sidious. Now, for those of you who don't know, .Sidious was the Dark Lord of the Sith, and he very successfully infiltrated the Galactic Republic as posing as a benign senator while truly being the malicious Dark Lord. And that is exactly what we aim to do with our project. Another very interesting fact I thought I'd introduce in the beginning of this talk is how PEsidious was in fact a solution that came out of a hack in the box challenge last year. So this was the HITB AI challenge, and that's really when Chandni and I got together and we developed this tool for that particular competition, and we were actually fortunate enough to win first prize for it. So when we heard there was a Hack in the Box conference, we were more than excited to present in this conference and share this with the broader HITB community. So before we get started, just wanted to give a huge shout out of gratitude to Dylan and the rest of the HITB group and crew for having us here for this talk. Right. So that being said, just a little bit of housekeeping before we get started. Now, we know that a lot of the stock is very heavy on the AI. So what Tony and I have decided is to keep things as high level as we possibly can throughout the talk so that everyone can benefit from it. Now, that being said, if anyone has any questions or would like us to elaborate more around a specific AI technology or anything in general, please feel free to shoot us a question. We will try our very best to address them when they come in. But if not, as Cooper mentioned, we are definitely going to be there to address all questions in the Q&A section at the end of the talk. And with that being said, I think we can move on to the next slide. So before we dive in, a very quick overview of what I'm going to be talking about, what we're going to be talking about for the next 1 hour. I'd like to start off this presentation with a very brief introduction of who we are, after which we're going to talk about PEsidious, what PEsidious is, and more importantly, why we decided to work on this project to begin off with. Following this, we're going to get into the implementation, that is how PEsidious really works, and a very brief project demo. Now, I just like to raise a point here. We're not going to do a live demo for this talk, and we're going to explain this during the end of this talk, why we've decided to keep it that way. Finally, PEsidious is an ongoing project. We are continuously developing this tool. We're continuously improving it and finding new ways to improve around this tool. So we'd like to conclude this presentation by just talking about a couple of things that we have planned for the future. That being said, let's move on to the next slide. So my name is Bedang Sen, and with me I have my friend and colleague Chandni Vaya. We are both incident response consultants with IBM's Expo's RS team. And apart from working in security, we have a lot of passion for, of course, AI. We love working with the data science. We have worked with microservices in the past. And what we find really interesting is really how all these technologies can be used together to solve each other's problem. Primarily because we are definitely security focused. We love leveraging these three key technologies to solve some of cybersecurity's most current issues and problems. So if any of you are interested in doing the same, or would just like to get introduced in this field of AI and security or microservices security or anything really, feel free to reach out to us. Feel free to connect to us on LinkedIn or any other platform really, and we'd be more than happy to sit down, have a discussion, and maybe even collaborate in the future. All right, so let's talk about PEsidious. Now, before I talk about what PEsidious is, I think it's very important to address a bigger question, why we decided to work on PEsidious to begin off with. And of course, the short answer is, it was one of the challenges from Hack and Box AI challenge last year. So that's what got us started. But it's really a lot more than that. Now, while we were conducting research, we found that over the past 2 decades, there have been numerous solutions which use AI to detect malwares or malicious activities. And due to this increasing popularity of the use of AIs, we notice a lot of malicious actors have started to leverage the same technology to attack those very same AI models that are used to block these malicious attacks. And they do this through a number of ways. There are cases where malicious actors poison these AI models using poisonous input. There are other ways. If a malicious actor knows enough about the way the AI model functions, it's very easy for them to circumvent those security mechanisms put in place to begin off with. So our key idea for this talk was to try and understand how easy it would be to use AI to mutate malware in such a way that an AV engine or an AI-powered AV engine would consider it to be completely benign. And that's what we're here to talk about today. So let's get started about what PEsidious is. Now, PEsidious is our malware mutation tool, which uses reinforcement learning and generative adversarial networks. Wow, that's a lot of heavy words over there. So let's try to break this down into what it really is. In a very simple sense, PEsidious looks at taking a malware file and mutating it using AI to make it appear to look benign to an AV engine. And that's all we're doing with PEsidious. But what's going to be interesting is how we go about doing these changes or how we go about doing these mutations. So I would love to dive right into how PEsidious works, but I think in order to make more sense of it, it's very, very important for us to really understand what those two heavy words really mean: reinforcement learning and generative adversarial networks. And with that, Johnny's going to talk more about reinforcement learning.
Hello, everyone. So what is reinforcement learning? Now, in its simplest form, reinforcement learning is basically teaching a machine how to navigate an environment to reach a goal by using a sequence of actions, right? And the way that the machine learns the right sequence of actions is by receiving some kind of a reward for every right move that it makes and receiving some kind of a punishment for every wrong one. Let's take an example, a very simple example over here. Let's say we have a dog over here, which is the agent, trying to navigate this environment, which is a maze, to reach its goal, which is the piece of meat. So right now, the dog acting as an agent is in tile number 1, which can be called the state of the dog, right? So the state of the dog is tile number 1. The different actions that the dog can take to move around in the environment are going up, down, left, or right. And this is all that the dog knows in the beginning of when the environment is initialized, right? This is all that the agent knows. Now, the first thing that the agent would do is that because it hasn't learned anything, what it'll do is just randomly move around and try to reach the piece of meat. Let's say, for example, it decides randomly to go down. The moment it does that, because it's a red tile and it's a wall, what we do is we give it a negative Q value. Now, what is Q value will make sense in a little bit, but the whole idea is that the moment the dog or the agent makes a wrong move, it should get a negative Q value or a negative reward. Now, let's say again, randomly, the dog decides to go right. Because it landed on the white tile, which is a right move, it will get a positive Q value. Again, let it make random movements. So it decided to land on a white tile. So we again give it a positive Q value. Again, it decided to go down and it landed on the red tile, which was a wrong move. So it will get a negative Q value. It will get a positive Q value, a reward for moving to the white tile. Same thing. And now, did you see what happened over here? It did move to a white tile, but instead of going down, it moved further away from the goal. So if we keep giving the same static reward for every time it lands on the white tile, the dog is not going to learn properly. So the way that the reward has to be assigned is based on how closer is the dog getting to the goal itself. So if we go back, right, when the dog was over here, if it had decided to go down, we would have given a Q value that comparatively would be more than the Q value it got when it decided to go up. And Q value is, the way that the Q values are calculated is just simple maths, right? It uses something called a Bellman equation, which is the core of what reinforcement learning is. But explaining the equation and explaining the maths behind it is a little bit outside the scope of this presentation. The only thing we have to understand right now is that Q value basically calculates the immediate reward that an agent would get for the action, plus the rewards that it will get for the subsequent future actions. So in essence, it's basically the closer that an action gets the agent to the goal, the more the Q value will be. And the further it gets away from the goal, the lesser the Q value would be. And every time it lands on the wrong tile or the wrong state, it would get a negative Q value. So as I said, initially the dog doesn't have any idea, right? It's trying to randomly move and see what are the different Q values for all the different actions. What eventually will happen is that after, let's say, thousands of these episodes of random episodes, or let's say 2,000 of these random episodes, the agent will build a table which is basically the Q values for every state and action pair. So for example, for tile 1, the dog will, or the agent will basically remember what is the Q value of going down, what is the Q value of going right, and what is the Q value of going left. So this is basically learning from the past experiences, right? When in the past it decided to go down, we gave it a negative 0.51 Q value and it stored it in the table. And after, let's say, as I said, 1,000 episodes, it will be able to build this entire table. And the next time when the learning is done during the testing stage, the dog will just look at, okay, I'm at tile 1, what action should I take based on the different Q values in my table? So because the action of going right has the highest Q value, I'll go right. And then it will land in tile number 2. And then again, it will refer back to the table. It will see that the Q value of going down is the highest. So it will decide to go down. And so on and so forth. And eventually it should land in tile number 34. And we can see in the table, the Q value for going right is the highest. So it will go right. And then again, from tile number 34 to tile number 35, it will get the maximum reward for the environment. So this is what reinforcement learning is, right? It's basically randomly moving around and collecting the Q values for every possible action. And then once the agent is done learning, referring back to those Q values to know what is the right sequence of action to reach the goal. Now, in this case, we can see the environment was quite small, right? It's a 6x6 square, with 36 of the total tiles. And the number of actions are just 4, right? Up, down, left, and right. Now, in reality, reinforcement learning is mostly used for video games or for chessboards. And when it comes to these environments, the video games, or let's say the AlphaGo game, the environments are very complex, right? It's not just a 6x6 square. It's not just 36 tiles. It can be thousands and thousands of possible states. And again, thousands and thousands of possible actions that the agent can do. And if the agent tries and builds this table, it will be quite inefficient in the terms of storage, because where will you store all that data? Where will you store the values for each possible state and action? On top of that, let's say if you do have the storage to store the table somewhere, referring back to the table for the state action pair, the time itself will be inefficient. So how do we replace this table with something more efficient, right? So if we look at the table, it's nothing but it's just a function, right? What a function does is that it takes an input and it does some calculation on it and it gives us the output. Now, the calculation part is what the dog should, or the agent should be learning. And what the first thing that comes to mind about how to build something that approximates a function that could replace this table is a neural network. What if, while learning, the agent, instead of building the table, actually tunes the weights of this neural network or trains the neural network to take our input and give the right output? In this case, to take the current state of the agent and give me the Q values for all the possible actions. And then I can just look at the Q value and see which action has the maximum value and then perform that action. So at the training stage, what I can do is let the neural network randomly select actions just the way that the dog was doing, and then use backpropagation to train the neural network saying, okay, so this is the Q value you gave me, but this should have been the Q value. So backpropagate the loss, train the neural network, and try and minimize the loss as much as possible. Try and minimize the difference between the Q value given by the neural network and the actual Q value, the right Q value. And once that loss, that difference is as low as 0.05, or that could be an hyperparameter, we can say that the neural network is trained. And this is what a simplified version of deep reinforcement learning is. And as Vedang said, deep reinforcement learning is just half of what PEsidious is. The second half is about generative adversarial network. And this is what Vedang will talk about.
Right. So generative adversarial networks, what are they? Now, as the name suggests, generative adversarial networks are generative models. And what this means is, unlike the other AI models you've typically seen in security, which you really use predictive or detection capabilities, which means they are used to predict data or detect data, a generative model, on the other hand, is used to generate data itself. And that just sounds super cool to me from the very beginning. So what a generative adversarial network is it's a class of neural networks that's used to generate data that closely resembles the internal structure of an input data. Now, I know I could go on and on describing what this is, but I think the easiest way to kind of explain what a generative adversarial network is and how they work is through examples. Now, right now, in the industry, GANs are most popularly used for image manipulation. So some of the most frequent use cases that we come across using GANs is, say, text to image translation. And what this means is you can go ahead and describe what you want an image to look like, and your generative adversarial network, or GAN, is actually going to generate an image for you. And you'd be surprised how accurate these images tend to be. Another example or use case is image-to-image translation. And again, as the name suggests, you can convert one image to another. And an example of this is you could take an image of a zebra and you can make it look like a horse. Another very interesting one is hand drawing to image rendering. So again, no explanation required there. And of course, I could go ahead and name a ton of different ones. But the one I want to talk about the most is what made GAN famous, or rather infamous, in the past couple of months, and that is deepfakes. So let's take a quick look at what a deepfake is and how it works. Now, in this video, you notice that we do have our input data set, which in this case is the speaker speaking. And you notice the different facial expression, body movement, eye movement that the speaker employs. On the other side, we have replicas of the speaker. The way this works is just using one source image, and then the replication video that you see in this video is using GANs. In another example that we'll see shortly, over here is we have the same thing. So here you have two input data sets, one of Barack Obama and one of Donald Trump. And again, you have a number of different target images. Some of them I can see is Vladimir Putin. We have Mona Lisa. And using the generative adversarial network, you can see how this AI model, these neural networks, are fully capable of replicating what the input video looks like. So that's what a deepfake is. But now let's try and understand how generative adversarial networks are used to generate these videos or replications. Now, what makes a generative adversarial network so interesting is the use of two competing neural networks. So it's basically AI training AI. And that's where things get really fascinating. So the first neural network that we have is called the generator. And the primary purpose of this neural network is to simply generate an output that closely resembles the internal structure of the input data while maintaining the features of the target data provided. So let's quickly flash back to the video. In that sense, the input data would be of, let's say, Barack Obama or Donald Trump, and the target images would be whatever the GAN was replicating. The other neural network that we have is the discriminator. And the purpose of the discriminator is to basically, discriminate between the target or the input data set and the target data set. So what it's going to do is it's going to look at the generated output, and it's going to try to understand whether the generated output belongs to the input data set or whether it's a fake. If the discriminator does decide that the generated output is a fake, it's going to provide some feedback to the generator. And the generator is going to take this feedback and retune the parameters of the neural network to produce a more accurate generated output. This cycle of feedback and retuning keeps repeating until the generator is capable enough to fool the discriminator. And that's how we get these deepfake images. Now, if we look at the process, the way the GAN works is before anything can happen, the first step is for the discriminator to train. The first step is to train the discriminator with the input data set and the target data set. And the objective of this is to just understand, for the discriminator to understand what does the input data set look like and what the fake data set looks like, to be able to understand where to place the generated output. Once the discriminator is trained, that's when we can finally feed in our fake data set or our target data set into the generator neural network. And while we do this, we also append a noise vector. Now, the only role the noise vector plays in this step is to help the generator randomize the value and give it a more efficient or effective generated output. And that's pretty much it. And then the process remains the same. The generator generates an output, and this goes to the discriminator, and the discriminator just checks whether it's a fake or belongs to the input data set. And until the discriminator is fooled, these two neural networks keep going on it in a loop. And that really is it. That's how a generative adversarial network works on a very high level. So now that we understand what a generative and adversarial network is and what reinforcement learning or deep reinforcement learning is and how they work, let's try to understand how we are using them in our project PEsidious. So the diagram that you see on the screen right now, on the slide right now, is a visual summary of PEsidious's implementation. And I know it looks very overwhelming at first glance. So let's do this. Let's try to break this diagram up into different phases or different steps to more clearly convey how this project works. The first step is going to be our feature extraction stage. Next slide. Right. Now, as much as I'd like for AI to be capable of just taking in a binary and running it through a model and mutating or creating mutated variants of this malware, I'm afraid it's not that simple. A binary is a very complex piece of data. And in order for us to train our AI models, we have to break this down into a simpler representation that our AI models can learn from and it can train on. And this simpler representation for us is going to be a binary representation, no pun intended, of ones and zeros. So let's take a look at how this happens. The very first step in our feature extraction step is to collect our data set. And this is going to be to collect our malicious and benign binary data set. Now, fortunately, there are a number of online repositories which host malware samples that can be downloaded for research or educational purposes. A couple of ones that we used were VirusTotal and VirusShare. For the benign binary data set, we unfortunately didn't come across any such online repository. However, it's not really that hard to get your hands on benign dataset. All you have to do is spin up a Windows virtual machine and then just run a script to collect all the binaries you can find in the system. And boom, you have your benign dataset. So now that you have both your benign and your malware dataset, you can move on to this next step, which is to extract all the features into a single feature vector. Now, when we talk about the step, the first question that automatically comes into my mind is, what kind of features are available in a Windows executable? What kind of features can I really collect? And second, out of all the features that I can collect, which features are going to impact my AI model the most? Again, it's very important to understand how these AI models work. You can't just dump everything into it and expect it to learn. You have to be very careful about, you have to be very smart about the kind of features you provide your model to learn from in order to train it most effectively. So we are going to address these questions in the coming slides. But for now, let's move on to the third point, which is, sorry, can you go back to the previous slide? Right, so the third point is to generate feature vectors for each of the binary data using the feature vector map. So once we have our feature vector map that we created in the second step, the next step is to create that representation for every piece of data that we've collected in our data set. So what this would mean is we would take a binary and we would more or less just convert it into a series of ones and zeros, where one represents the presence of a specific feature as per the feature vector map, and zero representing the absence of that feature. All right, so let's go to the next point and start answering some of the questions we raised in this slide. Okay, so when we raise the question, what kind of features do we have available? It's very important for us to look into an executable and try to find that answer there. So let's consider the example binary that we have here, an example.exe. On a very high level, a PE executable can be divided into two components. You have the header component and the section component. The header component contains sections like the DOS header, the PE header, optional header, data directory, and section tables. Now, the section table is a very important one. It contains a list of different sections and their locations in the section component. Now, when we go to the section component, this is where the main content of the binary resides. So this is where you'll find the code. This is where you'll find additional resources, such as any images used in the application, or icons used by the application, or any audio that's used by the application. So some of the different sections you'll find over here are code, inputs. Inputs is, again, a very important one we'll be touching in the next slide. And of course, the data that I just covered right now. So just looking at all of these different features, I think it's very easy to figure out that not all of this would be easy to convert into the representation we mentioned earlier. So the question then arises, which one of these would be most suitable to train our AI model? Now, based on prior research conducted, our own research, and numerous trials and errors, we narrowed down the most optimal features to these 6. The first one being section information. So this includes the number of sections with a non-zero value or an empty name, a number of sections with different characteristics. We include features of property of entry points, machine architecture, operating system. We include features of imports information and export information, such as DLLs and functions, as well as other header information, such as virtual size, debug flag, relocation, resources, and signatures. And we go through all these features while extracting them, while running through our entire binary data set, and we start storing every unique feature that we come across into a feature vector map. So let me try to explain that with a very small example. So let's assume I'm going through example.exe during the second step of the feature extraction phase, and I come across a unique DLL, say user32.dll, that I haven't come across before. As soon as I see that, I'm going to create an entry in the feature vector map, and I'm going to place user32.dll there. While again extracting the same binary, I come across another input DLL, which is the kernel32.dll. And again, I do the same thing. So now my feature vector map is this massive map which contains all the unique features that I've come across my data set. The next step is then to create feature vectors using this map for each of my data in my data set. So what that data is going to look like, or what those feature vectors are going to look like, is basically just the ones and zeros to fill up the values in this map. So let's consider another executable, let's say test.exe. And let's say test.exe does have a user32.dll. So we're simply going to plot a 1 in the vector location that corresponds to user32.dll in the vector map. And let's say it doesn't have kernel32.dll, then it's just going to remain a 0. So this is just to kind of illustrate what kind of data we're feeding our AI model. And this simple representation, while just consisting of ones and zero, is what we're using to represent the identity of the binary that we are training our model with. So now that we've understood what these features or what kind of data we're feeding into our AI, let's jump into the next phase, which uses reinforcement learning.
Okay, so now as Vedang said, what we did is we created a data set that is a representation of the malicious and benign binaries, right? But these data sets are just ones and zeros, one for an existence of the feature and zero for the non-existent. Now, to understand how deep reinforcement learning works with malware mutation, let's refer back to our previous example of deep reinforcement learning, which was the dog, the maze, and the meat. In the example of the dog, the environment was the maze, right? They were trying to navigate the maze. In this case, our environment consists of two things. First is a modifier. Now, again, when it came to the dog example, the different actions that the dog was allowed to perform was going up, down, left, and right. In our scenario, the different actions that the environment or the agent is allowed to perform are as follows. So what are the different actions we are performing on a malicious file to mutate it and to make it look more benign? Some of the things are we randomly add import functions and DLLs to the import table. We randomly add sections. We rename sections. For example, let's say the malicious file is packed, then most certainly it will have a section called .upx. What we can do is just rename it to something that sounds more benign or that looks more benign. Some other things that we do to change, let's say, the size, the hash of the binary is appending to existing section. Now, when we append to existing section, and if we append enough bytes, what it can also do is change the entropy. That is, if the section is packed, what happens is that, or if it's encrypted, the entropy is going to be high, right? The randomness of the section is going to be high, which can be an indicator of a malicious file. And if we add enough, let's say just enough zeros to the end of the section, what will happen is that the entropy, the randomness will keep lowering, right? It will keep getting less and less, and the malicious file will keep looking more like a benign file. Another thing we do is append random bytes, just change the size and the hash. We remove or add any signatures to the malicious file. We remove a debug flag if it exists. And we also try and pack or unpack using UPX packer, right? So these are the different actions that the environment is allowed to perform when it comes to solving the problem. So that was for the modifier. Now, what is the classifier? Now, in the case of the dog, what happened is that the way that the reward system worked is that whenever it landed on a white tile, it got a positive reward. And whenever it landed on the red tile, it got a negative reward. So how would the rewarding system work when it comes to mutating malware? It's simple. What we do is that we first get the score of the original malicious file. And then whenever we mutate the file, we again basically query some kind of a classifier, which can be your own trained machine learning model. Or in our case, what we did is we simply queried VirusTotal to get the score of the mutated malicious file. And then we just compare the score for the mutated malicious file with the original malicious file. And if the score, the number of engines that have detected the file as malicious has gone down, it's going to be a positive reward. If for some reason the mutated file has more score than the original file itself, then it's going to get a negative reward. So that was for our environment. The next thing in the deep reinforcement learning, the main component is our neural network. Now, again, what happened in the dog example initially is that to learn how to solve the maze. It was just randomly going around to try and see what are the different Q values. So right now, because this environment has just been instantiated, what happens is that the neural network has random weights for its hidden nodes, right? So it's just randomly going to select any kind of, is randomly going to give us output for Q values when it comes to actions. So let's say for the training stage, what would happen is that we'll take the malware feature data set, which would be the current state of the environment, right? Previously, it was just one single tile for the dog. In this case, it's basically a vector of hundreds and hundreds of features representing the malicious file. What we do is that we take the feature vector and we basically input it into our neural network. What the neural network, because it's just randomly assigned weights, is going to give us a randomly generated Q values for all the different actions. And what we'll do is just select the Q value with the max, we'll select the action with the maximum Q value. The next thing we're going to do is actually take the action into the modifier, take the malicious file, and for example, let's say the neural network said that the Q value for an appending random bytes is the highest. So the modifier is just going to go ahead and append random bytes to the sample. What it's going to do next is actually pass the mutated file back to the neural network to get the Q value for the mutated file itself. The reason we are doing this is, as I said, the core of the reinforcement learning is the Bellman equation. And what Bellman equation tells us is basically the addition of the immediate reward, which is the reward we'll get from the classifier, plus the rewards of all the future states, So what we'll do need is actually the future state too. So that's why we pass on the mutated and we'll get the Q value for the mutated malware. And what we do is pass all these three variables, the reward, the future state, and the current state, to our optimizer. Optimizer is nothing, but what it's going to do is actually calculate the Bellman equation, right? It's going to run a function that calculates the Q value using the Bellman equation. It's going to compare it to the Q value we provided from our neural network, and it's going to generate a loss. Loss is nothing but the difference between the Q value generated by the neural network and the actual Q value, right? The right value. And we just what to do is just pass the loss back to the neural network, and it's going to back propagate this loss and learn what mistakes it made the first time. Let's say the Q value that it gave for this malware feature was, let's say, append random bytes, right? But the optimizer told us that the actual Q value should have been add a signature. So what we do is we tell the neural network that the answer should have been this, and it basically takes the value, the mathematical value, and back propagates it through the hidden nodes. So what it will do is just adjust the tune itself to get the right answer next time. Another thing that we do is something called experience replay. This is very similar to how a human brain learns something. Let's say you want to teach a kid not to throw its sock around, right? Not to throw a sock or its clothes around. The first time it's throwing the clothes around, what we do is we give it a punishment. And the next time, hopefully the kid won't throw the clothes around in the room. And what we'll do is we give it a positive reinforcement. And the third time, what it's going to do, it's going to learn, okay, now I shouldn't throw the clothes around in the room because I want to get the reward. And it will put the clothes back in the cupboard or something. What is this? It's an experience that the kid has gone through, right? In this case, the experience would be a particular action or a particular modification to a malicious file. What we do is store that all the right experiences into a data store. And after every interval, let's say after every 10 right actions performed by the neural network, we pass it back to the neural network. We replay the experience for the neural network for it to learn better. Just like how our human brains learn better if the experiences keep replaying itself. So this is how a reinforcement learning agent would be trained for mutating a malware. Now, When we talked about the modifiers, some of the modifiers were very simple, right? We were renaming, no, let's that be. We were randomly adding bytes to the section. We were randomly adding bytes to the end of the file itself. We were adding or removing signature. But if you look at the first action that could have been performed is randomly adding inputs, functions, and DLLs. Now, what we did initially is we precompiled this list of all the possible DLLs and their functions from a Windows 32-bit machine. And we realized it didn't work that well. Not all the inputs and DLLs. For example, we also had a crypto library in there. Just imagine if it's a ransomware file and the neural network learns to add the crypto library into the malicious file. It's just going to make it look more malicious. And the reason that it's happening is because when it comes to adding inputs, we are just randomly selecting from the list. We are just randomly selected from the library of all the possible inputs and DLLs. Same goes for the sections. So what was the solution for this? The solution was simple. It was, what if we could get a list of imports, DLLs, and sections that we know would work for sure, that we know would definitely make a malicious file look more benign. Now, how do we get this list? This is where generative adversarial network would come in.
Right, so that brings us to our final phase of PEsidious' implementation, using generative adversarial networks to generate the most optimal feature list that can be then passed on to our reinforcement learning agent to mutate our malware. So let's take a look at how this works at a very high level. Now, you notice a lot of similarities with what we covered earlier with the deepfake example. So our first step is for feature vectors to be concatenated with the noise vector and fed into the generator neural network of the GAN. And once the GAN generates the adversarial feature vector, it goes through the discriminator and goes through that entire feedback loop. If you look at the diagram on the slide, you notice that the diagram is almost identical to what we looked at the deepfake. You notice an additional component in our generative adversarial model, and that is the introduction of a black box. So before we proceed, let's take a look at what that black box is and why we are using that black box. Next slide. Now, the purpose of the black box is very simple. It's simply to mimic the functionality of an AV engine. That is to classify a binary as being either malicious or benign. And of course, in our generative adversarial network model, it's not to classify the binary. But again, it's important to remember that it is to classify the binary representation, which is our feature vector. So what this black box is going to do is it's really going to try to understand if the feature vector or the adversarially generated feature vector is part of the benign feature vector set or if it's part of the malware feature vector set. And the way we do this is we train it with the most commonly known machine learning algorithms used by industry AV engines. And these are decision trees, logistic regressions, multi-layer perceptrons, random forests, and SVMs. So that's really what the black box is. Now let's go back and let's try to see how this fits into our implementation of GANs. Next slide. Okay. Now, if you look at this diagram, again, let's try to understand what's really happening here. So the first step for us in the process of running GAN is, again, to train our discriminator, but also our black box detector with the benign feature vector and the malware feature vector to classify between the two. And once that training is done, we then feed in the malware feature vector to start mutating through the generator. So we feed in the malware feature vector, again, concatenated with noise. And again, it's very important to remember this is just to improve the randomization of the generator and produce more optimal or produce more effective adversarial feature vectors. Once the feature vector is generated by the generator, it then goes and gets classified by the discriminator and the black box detector. And again, if the discriminator classifies it as being a fake, or in this case, a malware feature vector, then it provides feedback to the generator, which the generator then uses to, again, retune its neural network and produce a more effective adversarial feature vector, which is capable of fooling the discriminator. So until here, everything sounds exactly the same as what we covered earlier. So what's different? The first question that pops up is, if the black box detector is doing the exact same thing as a discriminator, why are we implementing a black box in this design? Additionally, a follow-up question could be, so if we are using a black box detector for whatever reason, then what's the purpose of having the discriminator? Why not just have one of them? The answer to this lies in the nature of the problem that we're solving. Unlike the deepfake case or a lot of the other use cases that we covered in the prior section, right now we are dealing with a problem use case of binary classification, which means at the end of the day, what we're looking at is whether the adversarial feature vector is classified as benign or malicious, and that is really it. When it comes to such problem use cases, the black box detector is a lot more effective in conducting that binary classification than our discriminator. So the purpose of having the black box detector here is to really aid the discriminator in coming to that conclusion of whether the adversarial feature vector belongs to the benign feature vector set or the malware feature vector set. So that explains why we have a black box detector. But the follow-up question would then be, why do we have a discriminator then if we are getting the output from the black box detector? And the answer to that is the black box detector's strength, which is its effectiveness in producing a classification output of 1 or 0, is the problem that it creates in training a GAN. A binary output like 1 or 0 is not sufficient information or sufficient feedback for the generator to retune its parameters. So, and this is why we still need a discriminator. Now, unlike the black box detector, a discriminator gives back a weighted output. So, and this weight output is crucial for the generator to understand how and where to really retune its parameters in order to improve the accuracy of the adversarial feature vector. So I hope that explains how the generative adversarial network works. Again, once the GAN works, the final output is going to be the most optimal adversarial feature vector, which is capable of fooling both the discriminator and the black box detector into believing that it is part of the benign feature vector set.
Great. So now that we understand how we trained our generative adversarial network and how we trained the reinforcement learning agent, the next step was to test it, whether it worked or not. And the way that the testing works, it's very similar, right? What we do is that we take a malicious file, we pass it to the generative adversarial network, and what we get is basically a adversarial feature vector for both inputs and sections, right? That would make that exact malicious file look more benign. We pass it as one of the actions in the modifier in reinforcement learning agent. And then we have our neural network trained that's going to tell us for this malicious file, these are the different actions that you can perform or that we can perform to modify the malicious file to make it look more benign. So what it would tell us, it's either add random bytes. So we'll add the random bytes, and then it will tell us, okay, now pack, and then we'll pack. It might tell us again to unpack because we can't go into the neural network and see how exactly it's working into the hidden nodes and the weights. So what it will tell us, okay, add a signature, add a debug flag, remove a debug flag. And then at some point, it's going to tell us to, again, randomly add inputs. And this is where the list from the GAN is going to help us, right? So we are going to randomly add it, but the list from where we are randomly picking these inputs is coming out of GAN. So we know that the list works the best for that malicious file. We know that even if we just add 1 or 2, it's going to get our malicious file more closer to looking like a benign file. So that's how the testing worked, right? Now, this is basically a graph showing how it went. So when we started off this project, which was, I guess, July 2019, to the time when we actually were done with, or at least the first part of the project was done for the challenge. So when we started the project, the whole idea was to make it as evasive as possible, right? So if the score of the original malicious file was 60 in VirusTotal, we want to bring it down to, let's say, 5 or 4. That was our expectation of how this all would work. And it did work, honestly. We were able to bring down the score from 60 to, let's say, 10 or even better, 5. And we were all happy and we were celebrating and it all was great. until we actually tried running the malware in a sandbox environment. And we realized that the malware is no more functional. It's not working. And what's the point of getting the evasiveness if it's not even functional? So then we started our second step of the journey, which was to bring back the functionality of the malware. This included, so first mistake that we realized was that the imports and just the imports that we were working with in GAN and where the imports that we were training the GAN with also included the imports from a 64-bit machine. So we had to filter out the 32-bit DLLs and 32-bit imports. The second is to the sample, the malicious sample, the virus that we got from VirusTotal, the sample. The samples itself had 1 or 2 64-bit malicious files, right? And because of that, the training of both the reinforcement learning agent and the GAN wasn't up to the point. So we had to filter out the 32-bit binaries too. Third step, what we did was we switched from Python to C++. Now this whole project is based on Python. It's programmed using Python. And there has been research done on something very similar, right? How to use AI to mutate a malware. And all the research papers use this one library called Leaf in Python. And we went ahead with it too. And then we realized Leaf is what was breaking the functionality of the malware, right? When it was mutating it and trying to rebuild the binary, it wasn't able to do so properly. So we used C++ instead. So that's for maintaining the functionality. Now for improving the performance, what we did is that we used a combination of machine learning models. So as Vedang talked about for his black box in GAN, instead of using just one, let's say, random forest algorithm as a classifier, we used multiple of them. Initially, the whole idea was to just scope it down to backdoors. So the project just worked on mutating backdoors. And if we tried mutating ransomware, it did work, but not that well. So we tried to train our models to learn how to mutate other diverse malware families too, right? On how to mutate a ransomware, how to mutate, let's say, Trojan, etc. And how did we test it? How did we know that the model right now that we have is the best that it could get? What we did is we actually compared it to mutating the file ourselves. So what we did is instead of using AI to mutate the file, what the dog did in the beginning, right? We randomly selected actions, we randomly selected imports and sections, and we mutate the file with that. And we checked the score against VirusTotal to see what's the score we are getting. And as soon as the AI score was better than that of the human, we knew that the AI has potentially reached its point, right? Is potentially a better solution right now. It can get better, but that was our first step to reach there where it performs better than a human being. That was for the testing. Now let's get into the project demo. So right now what we have is PEsidious is a console program, right? So what you do is just run PEsidious with a malware file that you want to mutate. In this case, it could be a backdoor or right now a ransomware. So let's see what it would do. Oops. Right. So we run our Python application against a malicious file. And it would basically start querying the neural network for GAN and then the reinforcement learning agent to see what actions to perform. So we can see that the neural network for RL agent is performing different actions. It's again trying to pack, which in this case, it would fail. If it's already packed, we are just using one packer, which is the UPX packer, right? So it's already packed. It's not going to pack again. It's going to append random bytes. And you can see if it's going to try adding a section, the section name comes from a list that has been compiled by the GAN. Same goes for the inputs. This is great, right? Now we got the mutated malware. What's the next step to know if it's working or not? So what we did is we took this mutated malware and we actually ran it in a cloud-based sandbox environment, which is any.run. So if you want to try it out, what you can do is just go to these links and you can see the functionality of the original malware that we used with PEsidious and the functionality of the mutated malware. And you'll see that the functionality remained, right? It was 100% functional, the same functionalities. Let's have a look at that. So this is the original malware, right? So we can see what the original malware is trying to do is that it's trying to connect to a C2 server, right? The domain is Amazon and these are the threats. Now this is the original malware. Let's go to the mutated malware. You can see that the hash is different, the MD5 hash. And we come here and we see the same functionality, right? So it's again trying to connect to a C2 server somewhere. If you want to look at the detailed report, you can go to the text report over here and you'll see how the process is started, the registry keys written, changed, or read are all the same. So everything is same about the malware except for the scores. So this is the score for the original file, which is the 66 AV engines detected. And this is the score of the mutated file, 37 out of, let's say, 67 engines detected. Again, it didn't go down to what our expectations were initially, which is 5 or 10, but it did go down by almost half, and the functionality was intact. Now, if you go to the details tab for the original and compare it to the details tab of the mutated malware, you'll see all the different imports and sections that we have added during the PEsidious thing. So we can see that we have added random sections, we have renamed sections, and we have added a bunch of imports. And this was our demo. What is this it? Is this it for our project, or is there more coming? Yes, there is definitely more coming. First thing is we definitely still need to improve the evasiveness. So we want to go down from 66 to, let's say, try and go down to 20 or 15 if possible. At the same time, make sure that we maintain the functionality, right? We don't want to just improve the evasiveness and not have the malware function. There's no point for that. And what will we do, right? What will we do with all these mutated samples, right? We are from the blue side. We work for the defenders. So how will we use these samples for our benefit? What we can do is we can help the next generation antivirus systems to not only detect the original samples, but also be able to detect the mutated one. It's just like deep fake, right? If, let's say, if we see an image, we would want to know that if the image is a real one or is it a fake one. Same like that. The antivirus engine should be able to detect if the file is actually benign or is it just a malicious file looking like a benign file. And that is it. But before we jump into the Q&A, we are actually going to present the same tool in Black Hat Asia during the Arsenal. And we are hoping to make our demo more interactive with a lot more features and hopefully make it a GUI application. So please, as it is virtual, please do make sure to come and attend that too. And that is it for the presentation, and it's time for Q&A.
Okay, well, we've got 4 questions here. The first one is, what tools did you use to extract the features from the binaries?
So again, as we said that the whole project is based on Python. There was a library called a PE file that helps us extract different information from the binary.
Okay. The other question was, second question, how big was your data set and are you releasing it?
Dataset for the malicious file was, as we said, is from VirusTotal and VirusShare. And if you have a good reason, VirusTotal will be able to give you access to the same dataset. As for the benign file, I think Vedang would be able to explain that better.
Yeah, again, so while we were conducting this project, while we were building this project, we didn't really come across an online database that stores benign files. But like I mentioned during the talk, it's actually not that hard to get your hands on a collection or create your own database of benign files. All you really need to do is spin up a fresh VM of Windows 7, preferably 32-bit. We're still testing it out in 64, but whatever you're comfortable with, and you can get them for free from the Microsoft site itself, so it shouldn't be too big of a hassle. And then you can just run a script to kind of scrape through all the binaries that you find in that system. And that's what we did to create our own database of benign binaries. In terms of the size, I can comment on the size of the number of benign binaries. I think from our fresh install, we'd collected around 63,000, if I'm not mistaken. I think that's the number that pops to my head.
And as for the malicious files, so what we did is that, again, we requested VirusTotal, and because we had a good reason, which was the AI challenge, they did give access to their entire malicious file database. And they had the malicious file from, I think, 2016 to 2020. The only issue that we faced is that the malicious files weren't classified based on different malware families. So what we had to do is go through the malicious file, try to see what family it belongs to, and then filter it out based on which of these files are ransomware, which of these files are backdoors, and then train the machine learning models accordingly. And as for the size, I think the size was quite less when compared to benign files, because we had to filter it based on ransomware and backdoor. So when it came to ransomware, I think it was around 15K. But what we did while training is that we actually trained with those 10,000 plus, even if we needed more data, we even trained our neural network with the mutated files itself. So we double mutated, if that makes sense.
Okay, then the next question is, does it work the same on 64-bit?
Right now, PEsidious is just for 32-bit applications. So no, it doesn't work with 64-bit, although that would be the future plan. And yeah, but it wouldn't be that hard. Once we have the parameters set right, once we have the hyperparameters for AI, for the different neural networks for both reinforcement learning and GAN, we should be able to use the same training and testing stage for 64-bit too. We just have to collect the data. But getting the data set for the malicious samples would be a little hard, because as far as I know, VirusTotal only gave me access to the 32-bit one.
Clear. And then have you considered incorporating the killing framework or other analysis tools into your pipeline for feature extraction?
Sorry, could you repeat that, the last question?
Have you considered incorporating the killing framework or other analysis tools into your pipeline for feature extraction?
I'm not sure. So we haven't looked into anything else for feature extraction, but a very interesting point. I'm not sure if this relates in any sense to the question, but one of our to-dos for future work is to kind of replace the black box that we have with something like VirusTotal. So rather than relying on our own made machine learning algorithms to detect malicious from benign, we would rely directly on VirusTotal, which would be scoring that against a number of different AVs. And we're hoping that would improve the performance of our entire tool set.
And I think there are analysis tools that can also extract the features for us, but PEfile does it pretty well. It's easy to use, and because it's Python based, we can automate the whole thing. So yeah, we went ahead with the PEfile.
One of the questions that was asked fairly early on was, does the modification result in an unstable malware binary, or does the exploit functionality remain the same? I think you pretty much covered that in the talk. Don't know if you want to elaborate, but
it would depend on the number of modifications you are making too. So as I said early on, when our whole focus was on just make it as evasive as possible, the total number for the modifications made were up to 160 or 200. And then we realized the more modifications we make, the lesser chance that there are for the malicious file to remain functional. So after a lot of trial and error, we realized that the number 80 works the best. So after 80 modifications, after 80, we don't let the environment make any more modifications, no matter what's the score. If it's reached to the 80 threshold, it doesn't make any more modifications.
Thank you for that. And the last question I've got is, how much work would it be to add more file types, say Android malware or OS X?
Well, we'll need to understand the structure of the files. It would be like an entire different project, because we'll have to again create the data set from the very beginning. We'll have to train the machine learning models from the very beginning. But as I think if you understand the structure well, it should be fine. And we still would need support for extracting features. We would need support for the classifiers. While when it comes to PE32, there were already, for example, as I said, PE file that was already existing there to extract the feature. There was another library called Leaf that I talked about, which was able to modify, even though was not able to keep the functionality intact. There was a library to play around with the PE32 files. But I'm not sure if there are similar support frameworks for the other types.
Yeah. Also, if I may add on to that, in my opinion, I can see one challenge rising up the others, and that comes in the feature extraction phase. Now, and this really stems from the fact how different PE files are from, let's say, ELF files in the Linux, or Android files, or OS X files. And right now, our neural networks, both reinforcement learning as well as the generative adversarial networks, are built on the features that we have extracted, built around the structure of a PE file. So to have these feature vectors kind of incorporate all of them in the same model, that would make it very challenging for the neural network to really learn. And in my opinion, so it really depends. You can always fine tune it a lot more, but it would be a lot harder compared to having a single AI algorithm working, or AI model rather, working on these independent file types.
Okay, well, thanks guys. That is the full list of questions. We are a little bit over time, but hey, it's the last talk of the day, and it was a nice topic to end on anyway. So again, thank you very much for your talk.